Hi there, and welcome to this lesson on Further Pure Mathematics 2. And in this lesson, we're continuing to look at how the locus of a complex number can be represented on an Argand diagram. Now, in a previous lesson, we discovered that most loci problems can be approached by two methods. You can either approach them geometrically or algebraically. Now, there are merits with both approaches, but frequently the algebraic method is the easier one to understand and follow through with. In this lesson, we'll be considering some more complex loci. And we'll begin by thinking about loci of the form: the modulus of z minus some fixed point a is equal to a constant times by the modulus of z minus a second fixed point b. What's this saying? Well, geometrically, it's saying that the distance of z from a is a constant multiple of the distance of z from b. So, for example, you might have the modulus of z minus 0 plus I is equal to 2 times the modulus of z minus 3 minus 2i. And that would be saying that the distance of z from 0, 1 is double the distance of z from 3 minus 2, which feels like quite a complex idea, and you'd think that the locus might be quite complex. Surprisingly, it isn't. The locus of the points defined by this type of relationship is always a circle. And we can find the Cartesian equation of the circle, we can find its center and its radius, using the algebraic method that we used in a previous lesson. So we'll have a go at doing that. Example 1, find the Cartesian equation, the center and the radius of the circle, defined by the relationship, the one that we were just looking at. The modulus of z minus 0 plus I is equal to double the modulus of z minus 3 minus 2i. And just to remind you, the way into the algebraic method is by first of all letting z equal the general complex number x plus yi. I'll let you have a go doing this yourself first, pause the video, and then come back to me again when you're ready. Okay, let's have a look at this. So as I said, you begin just by substituting z equals x plus yi into the question, which gives you this. We then collect together the real and the imaginary parts in each modulus, which gives us that. And we then use the basic definition of a modulus to get the square root of x squared plus y minus 1 squared is equal to 2 times the square root of x minus 3 squared plus y plus 2 squared. To get rid of the square roots, we square both sides. Then we square the brackets. Multiplying out the brackets and collecting together the terms will give us that. Now, all of those terms are multiples of 3. So the easiest thing to do at this point is divide by 3. And the equation simplifies to that. The standard form for a circle, we'd factorize these pairs to get something like that: x minus 4 squared plus y plus 3 squared minus 20 equals 0. And the standard form for a circle has the minus 20 on the other side of the equal sign. So the most usual way to write the equation would be x minus 4 squared plus y plus 3 squared equals 20. And the reason why that's the normal way is because if you do write it like that, then the center and radius of the circle can just be read straight off the equation. The center will be 4 minus 3, and the radius will be the square root of 20. Okay, we've looked at loci of this form. We'll now look at loci of the form: the argument of z minus a over z minus b is equal to a constant angle, theta. The way to get started on this is to use the rule that you hopefully remember with arguments, which is that this means exactly the same thing as the argument of z minus a minus the argument of z minus b is equal to a fixed angle theta. Now, what is this saying? Geometrically, this is saying that the angle between a point z and two fixed points a and b is a constant. Now, when does that happen? Well, it only happens if a and b are the end points of a chord in a circle, which means that z is going to be tracing out not the whole circle, but an arc of a circle. And it begins at A, goes round to B, so it begins at the first point, goes to the second point, anti-clockwise. The size of theta matters. If theta is less than pi by 2, then the locus is a major arc of a circle. If theta is bigger than pi by 2, then the locus will be a minor arc of a circle, less than half of the circle. If it's exactly pi by 2, then the locus will be a semicircle. Okay, let's have a look at an example. So example 2, given that the argument of z minus 6 over z minus 2 is equal to pi by 4, sketch the locus represented by the point z. Now these two numbers will normally be complex numbers. In this example, they're both real numbers. It means that they'll be on the real axis in the Argand diagram. This does make the question a little bit easier to do. But in general, they could be any complex number. Anyway, I'll let you have a go at doing this yourself first. So pause the video and then come back to me again when you're ready. Okay, let's have a look at it. Well, we'll look in detail at what's going on here. What this is saying is that given the points 6 and 2 on the real axis, the point z is constrained to be at those places where the angle between the line joining 6 and z and the line joining 2 and z is always equal to pi by 4. So if we have an Argand diagram, we've got the point here at 2, 0, which is B. A here is 6, 0. And the point z we can draw anywhere as long as the angle that we get between z and B and z and A is exactly pi by 4 radians. So we could draw it there, we could draw it here, we could draw it here, and so on and so on and so on. But what you can already begin to see is that these possible locations for z are starting to trace out an arc of a circle. And if we continue the whole way, then we get something like that. So that is the locus represented by the point z. It's the major arc of a circle. We do need to take a little bit care if you're going to write down exactly what you have. So what we have is the major arc from 6, 0 to 2, 0, but it does not include the 2 endpoints. So you have exactly the same issue as we had with half lines, where the endpoint was not included. It's easier to see why the endpoints are not included here. If you did have the endpoints, you'd just have a straight line. If you just got a straight line, you don't get an angle, so you don't get the pi by 4 radians. So when you write down the answer, you do need to make sure that you make it clear that the 2 endpoints themselves are not included in the locus. Okay, part 2, find the Cartesian equation of this locus. And we'll do this by 2 methods. We will do it both by the geometric method and the algebraic method, just to see how the 2 methods look. Now, the geometric method is quite hard to guess, but I'll let you have a go at guessing it. So if you want to have a go, pause the video now, see if you can do it, and then come back to me when you're ready. Okay, let's have a look at this. As I say, the geometric method is hard to guess. The starting point is hard to guess. What we do is we use the circle theorem that the angle subtended at the center of a circle from any given arc is double the angle subtended at the circumference. So in this case, if we draw the circle, the center of the circle C, then what we know is that the angle that we get here at C will be double this angle. So if this is pi by 4 radians, which we know it is, then the angle at the center will be pi by 2 radians. Now, once we've done that, we get a triangle here, BCA. And we can look at that isosceles triangle and just use standard geometric methods to calculate both the center of the circle and the radius of the circle. So there's the triangle. There's A, B, and C again. Pi by 2, we said, was the angle here. The first thing we do is cut this triangle in half, drawing the perpendicular bisector of AB. So this angle gets cut in half, so we get pi by 4 here and pi by 4 here. Now, the fact that we get pi by 4 radians, 45 degrees, that is very useful because we know that this angle is 90 degrees, which means that this angle here must also be 45 degrees, pi by 4 radians. So we get an isosceles triangle. Both of these right-angled triangles are isosceles. Now, that does turn out to be useful in the algebraic method as well. It is just helpful that this angle is 45 degrees, pi by 4. So this is pi by 4. This is also pi by 4. That means you've got an isosceles triangle. So we know this is 2 because the distance from 2, 0 to 4, 0 is 2. That means that the vertical height must also be 2 because we have an isosceles triangle. That means we can find the radius of the circle. It'll be the square root of 8, which is 2 root 2. And it also means we can find the coordinates of the center of the circle. C is directly above this midpoint, so the x-coordinate of C will be 4. And we know the vertical distance is 2, so the coordinates of C must be 4, 2. Now we know the center is 4, 2. We know that the radius is 2 root 2. At that point, you can write down the Cartesian equation of the locus, which will be x minus 4 squared plus y minus 2 squared equals 8. Again, just from 6, 0 to 2, 0, but not including those 2 endpoints. What about the algebraic method for doing exactly the same thing? Now, having said at the beginning of the lesson that the algebraic method is usually easier, it's not much easier in this case. The starting point, as always, is we let z equal the general complex number x plus yi and substitute that into the equation. Okay, I'll let you have a go at doing this. Pause the video and then come back to me again when you're ready. Okay, let's have a look. So that is the question. Substituting z in, we will get that. Collecting together the real and the imaginary parts, we will get that. Now, it's this next step which is not obvious. It really does help if the denominator of this fraction is a real number. Now, the way you make the denominator of a fraction a real number, when you've got a complex number on the top and a complex number on the bottom, is to multiply by the complex conjugate of the denominator, both the top and the bottom. So what we do at this point is we multiply the top and bottom of this fraction by the complex conjugate of the denominator. When we multiply out those brackets, that will simplify to that. Now, splitting up the real and the imaginary parts gives us that. The argument of this is equal to pi by 4 radians. Now, again, it does turn out to be useful that we've got pi by 4 because the inverse tangent of pi by 4 is exactly 1. The way we'd be calculating that using the argument is doing the imaginary part divided by the real part. Now, if the imaginary part divided by the real part gives us exactly 1, that means that the imaginary part and the real part must be equal to each other. Otherwise, we couldn't get 1 for the answer. So as with the geometric method, it just turns out to be very helpful that this angle is exactly pi by 4 radians. So that's where we've got to so far. We know that these two things must be the same as each other. Now it's straightforward algebra from here on. The denominators are both the same as each other, so you can just say straight away that the tops must be the same as each other. And then we're very nearly at the equation of the circle. So tidying that up, again, it'll give us x minus 4 squared plus y minus 2 squared is equal to 8, which is the same answer as we got using the geometric method. Okay, that gets us to the end of this lesson. If you have the textbook, then turn to page 61 and have a go at exercise 4B. Thank you very much for listening, and cheerio.